Hello everyone, so this presentation is going to be about quantum golden collision finding, and this is joint work with Jaques. So what's in there? We're going to study generic quantum algorithms for golden collision search, which basically means meeting the middle problems. So the golden collision problem can be phrased as follows. We have a random function. It has many collision pairs, and we assume that there is a golden collision among them that we can recognize, and we want to find it. So this can be applied to the security of the NIST post-quantum candidate SIKE, which is now selected in the second track. The algorithms that we're going to obtain achieve only polynomial speedups, quadratic as best, but it's necessary to precisely estimate them to have more confidence in the parameters that we are going to use. So at Crypto 19, Jaques and Chang studied the non-quantum algorithms for the problem using reverse search and Chinese clue finding. They use two cost metrics, the gate count and the depth switch product. So we're going to keep these cost metrics, but we're going to introduce new algorithms and improve parallelization trade-offs. So this will enable us to give new complexity estimates for SIKE, including also the NIST levels 2 and 4, and this will improve over the work of Jaques and Chang. However, the parameters of SIKE that were proposed remain secure in these metrics. All right, so I'm first going to make a little introduction to the problem, how it applies to SIKE. Then we're going to see quantum algorithmic frameworks that we use to solve the golden collision problem. So we're going to see quantum search, quantum walks. And then we move on to the new ideas. So why does this apply to SIKE? One of the basic problems on which SIKE is based, on which the security of SIKE is based, is finding a path between two curves in a supersingular isogenic graph. If we forget that these are curves and that the edges are isogenous, we just have a graph and we want to find a path between 2 points of a certain length, which means looking for a collision between a path that starts from one of the curve and a path that starts from the other curve. And this is meeting the middle problem and a golden collision problem that we can solve with these algorithms. So classically, if we have a function we want to find the golden collision, we can just query a lookup table of this function, sort the table. We find all collisions, it takes time n, memory n. If the memory is limited, the best method to use is Van Schott-Wiener distinguishment technique. It has a best time memory trade-off. Our cost metrics in the quantum setting are based on the abstract model of quantum circuits. So we write quantum algorithms in this model where we have a pool of qubits on which we're going to apply quantum operations from a standard gate set. And we build a circuit like this, pretty much like Boolean circuits. We're going to consider two cost metrics. The first one is the total number of gates, and the second one is the product of the depth and width of the circuit. And the difference is basically the cost of the identity gate. In the gate cost, if you consider the gate cost only, it's as if keeping a qubit idle costs nothing. So the identity gate costs 0. And the depth width cost, it's as if having a qubit at some point, even if you don't use it, is costly. So the identity gate costs 1. On this example here, I have a circuit. Let's forget what it does. It has 7 gates. But the gates are applied sequentially. So the depth switch cost is 7 times the number of qubits that we're using, which is 9 here. So you can see that the algorithms that we're going to have in both metrics are going to be different. And they're going to be optimized differently. So let's see now some quantum algorithms that solve the problem. And the first thing that we can do is to apply quantum search. Imagine that we make a classical search among all the pairs until we find the golden collision. It's like a search space, and there are a few solutions. In our case, there is only one, although on my drawing there are 4. We just pick an element at random. It's not a good one. But we pick another one, still not a good one, not a good one, but this one is. So we have found a solution. We simply need an operation that picks elements and an operation that tests elements, and we repeat that. In the quantum setting, we do things differently. First of all, the quantum search is a stateful procedure. So it starts from a state, a quantum state that represents that is a superposition over the whole search space. So it's like a distribution over all possible elements. And the operations that are also iterates will progressively transform this superposition and move towards a superposition over only the solutions. So in our case, the one golden solution. And the number of iterates we have to make is the square root of the number of classical iterates we would have to make in the classical search. Which means that in our case, with a search space of size n squared and one solution, we need a time n. Memory is negligible, so the gate cost is n and the depth width cost is n. And this is the well-known quadratic speedup of quantum search. However, if you start to set a depth limit which is lower than n, then you run into trouble because this operation is sequential. And if you have this sequential circuit and you want to reduce the depth, then you're going to increase the gate cost. Now, in order to solve the golden collision search problem with a better time, we need to use quantum walks. The best quantum algorithm, if you consider time alone, is given by Ambani's element distinctness algorithm, which was adapted to the claw-finding setting by Tenney. And it's like analogous to the classical time equals n, memory equals n, in that it gives a time n to the 2/3 and a memory n to the 2/3. And if you re-optimized it with classical operations, you would obtain this classical trade-off. So it can be rewritten in the MNRS quantum walk framework, which only requires to write operations, specific operations, that we can plug in into this framework and obtain an algorithm, pretty much like quantum search. So we're going to consider a graph, but actually it's a very abstract representation. In practice, the state of our walk is just going to be a list of elements. This graph that we consider as a Johnson graph, it's regular, it's undirected. The vertices are subsets of size R, the parameter, of the domain, with all the images, of course, computed. The vertex is said marked if it contains a golden collision. Since we have computed all the images, we can see that. And two vertices are connected if we go from one to the other by changing a single element. So we pick an element, remove it, and we add another one. And this is a Johnson graph. We're simply going to walk on this graph. So let's first do a walk classically. Classically, we start from a vertex, so a list of elements. We move, change elements in the list. We move to the neighbors until we find a marked vertex. Meaning we have a list, we change elements until we find the golden collision, until it appears. Here it is. So in order to estimate the cost of this random walk, we need to estimate how much it costs to set up a starting vertex, to move from one vertex to one of the neighbors, and to check if a vertex is marked. So setting up a vertex means simply querying many elements. Moving to a neighbor is going to be easy. Checking is also going to be easy. Now the time complexity is going to depend on the time to set up, the time to update a vertex, time to check, and it depends on the proportion of marked vertices, in the sense that we're actually repeating a sample of a uniform random vertex in the graph. In order to resample a uniform vertex, we need to update, we need to perform, to move on the graph at least 1/delta times, where delta is a spectral gap. And actually in our case, 1/delta is R for a Johnson graph, which means if we want a new uniform random vertex, we need to replace all elements in the list. And we do that 1/epsilon times, because epsilon is the proportion of marked vertices, which means we resample the random vertex, and after some time we fall on a marked one. Now in the quantum setting, things are analogous but different in the same way that quantum search is different from classical search. Now we're going to start from a uniform superposition over the whole graph. so it's a big one. And we're going to move it with iterates again towards a superposition of our marked vertices. Like this. Now the setup is going to require to create a superposition over all vertices. So it's basically the same cost as before. As in quantum search, the number of walk steps we need to perform is lower. It's square root of 1 over epsilon instead of 1 over epsilon. And the mixing time is accelerated. Instead of having to perform 1 over delta updates, we need to perform square root of 1 over delta quantum updates. Now, if we just plug in the numbers in this time complexity formula and assume that the update runs in time polynomial in R, in logarithmic in R, then we have we just have a square root of our term here. The probability for a vertex to contain the golden collision is just R squared over n squared. And this is the number of walk steps, and if you optimize everything, you get R equals to n to the 2/3, and you get the time complexity of Ambéni's algorithm and Tanny's version. That is, if you have quantum RAM. The problem is the update operation. The classical update has this list and takes a random element in this list and it adds a new random element in the list. Fine. The quantum update needs to remove an element from the vertex, but any of them in superposition, and to add a new element to the vertex in superposition. What's really important for us is that the vertex, the list that we have, must be kept sorted at all times, so that we can easily detect the golden collision. Which means we need somehow efficient memory management, what we have classically with random access memory, and what we have quantumly if we have quantum random access. And quantum random access, if we want to formalize it, actually involves a quantum gate which has an arity R here. So a gate that is spanning all our qubits and is still of cost 1. And this is a very powerful assumption. And if you assume instead that you have only gates of bounded arity, which is well, the case nowadays, things are pretty different. And actually, Ambéni's algorithm doesn't work anymore. So in Crypto 19, Jaques and Chang remarked that if you re-optimize everything, the only thing that you're going to gain is a polynomial factor. And it's actually the square root of the time you need to evaluate the function h. So this is the only thing you gain against Grover's algorithm. Which is why we need to adapt our algorithms to not use quantum RAM anymore. Let's have a look at this update cost. Before we had the cost of computing this new element to add it to the vertex, and adding it to the vertex was done in time polylog of R with an efficient memory management using quantum RAM gates. Now, the memory management is going to cost R, and it's incompressible. This is the size of the vertex, we must pay it at all times. But now, computing h, so computing this new element, is something that is much smaller. It's still a polynomial cost. So our idea is to push more cost into this term here. And now this means that we're going to compute a new element, but a special one, like a distinguished one. Which means we don't walk on the graph, on the big Johnson graph anymore. We don't have lists of any elements in our vertices. We have distinguished points now, and we're going actually to work on a subgraph. If we do that, we can expect that the probability for a vertex to be marked is going to be higher, and we have to work less. And we have something that balances more nicely. So we used two different definitions of distinguished points, which are actually quite the same. The first one is using function iterations, as in Van Hoschel-Wiener's algorithm. Because actually Van Hoschel-Wiener can be rephrased as a classical random walk. And if you take this classical random walk and you make it quantum, you obtain a quantum walk algorithm in the MNRS framework that works pretty well. In this presentation, I'm going to focus on the second definition, which simply uses subsets of the domain on which the function h evaluates to some prefix, has some prefix. Actually, both ideas gave us the exact same complexity, so we just need to see one here. We define a proportion of distinguished points and we work on them. So the time complexity is changed. Now the setup requires to create a vertex, a list of all distinguished points. And to create a distinguished point, we use Grover's algorithm, so complexity of 1 over square root theta. In order to sort the list, we use a sorting network. This is fine. As I said, the probability to find to have marked vertex is increased because now we're only working on distinguished points. Well, that is, if the golden collision occurs on a pair of distinguished points, because it may appear anywhere. The spectrograph stays the same, and the update, as I said, is going to have a factor 1 over square root theta and a factor r. And the checking cost is still trivial because we can still check efficiently if our list or sorted list contains a golden collision. Now, this is only a single walk, and it assumes that the golden collision is there. If it isn't, we won't find it. And actually, since we don't know for which set of distinguished points it did occur, we have to test all of them, which means we take this algorithm and we put it in a giant quantum search for the good subset of distinguished points. So we take this cost and we multiply it by a factor of 1 over square root theta. And if we do that, and if we optimize everything with theta and r, we get a gate complexity of n to the 6 over 7. Actually, the trade-off curve is the same as in Ambani's and Tainis algorithms, but it just stops earlier at r equals n to the 2 over 7, which means if you use more memory, this is going to cost more. You're going to move away from the trade-off curve that we had before. Turns out also that this algorithm is almost always the best in the gate cost. But it's in the gate cost only, and actually for the depth width cost, we needed another idea, which is the following. We're going to use the parallel Grover search of Bills et al., which relies on the following idea. If you have p quantum processors that are communicating freely, you can use each processor to store an element, and the p processors are going to store a memory of size p in total. And by simply communicating with each other, you can emulate p individual accesses of each processor to the whole shared memory in a walk time which is polylogarithmic in p. Or this allows a very efficient time-space trade-off for golden collision search in Bills et al. paper. But this works only if the processors have free communications. And in our case, this works only if the qubits in the circuit can communicate freely with each other. If the interactions are restricted to a local grid, in Bills et al. Paper, you need to pay an overhead, which is basically the time to sort on this grid. And in our case, we found that we could use distinguished points to amortize this communication cost, which means we can still parallelize almost perfectly, have a depth width and a gate cost equal to n, with communications on the local grid, and this works until the depth is equal to square root of n. Below that, it starts to be a bit too shallow and the gate cost is going to increase. So about security levels for SIKE, then let's define these security levels depending on exhaustive search on AES and finding collisions on char hash functions, so breaking symmetric key primitives with quantum algorithms. And there is a limit on the maximal depths that you can use in quantum circuits from 2 to the 96 to 2 to the 40. So in our case, we wanted to compare with levels 1, 3, and 5, but also 2 and 4. So we studied the algorithm of Xiaoyu et al. Of AsiaCrypt 17, which is the best quantum collision search algorithm if you don't have quantum RAM. And we gave gate and depth width estimates for this for levels 2 and 4. And we also improved the parallelization of this algorithm, so we could give better estimates. And in general, we evaluated the gates and depth width costs in the local setting, so in the local communication grid, for our algorithms for all SIKE parameters. So to summarize, in this paper we saw that quantum walks could still give an advantage in the gate cost even if you don't use quantum RAM. We also thought that in the depth width metric, the parallel Grover search has an almost perfect parallelization even if you assume only local communication constraints, thanks to distinguished points. The security of SIKE that we estimated with the new results is going to be lower than estimated in Jaques and Sheng Crypto 19, but it still meets all the list levels that it was intended to match. The paper is available on this ePrint report, and we also had a Python script to compute all these security estimates for the different algorithms. Well, that's all for me. Thank you for your attention.